Okay, this question from the fall 2014 exam is to draw the stereochemistry of this SN2 reaction. So let me redraw this down here a little bit clearer. Well, we have a cyclohexane ring. We have off of that a carbon with a hydrogen on the dashed wedge, a methyl group on the bold wedge, and the leaving group, which is iodine. And we're going to add to that a C triple bond N, where the C is N minus. So that's our nucleophile. So what's going to happen in this reaction is that the CN minus is going to come in and attack the carbon down the trajectory of the CI bond and kick it out. So the transition state that I wrote here just took this molecule and rotated it rotated about 30 degrees to make the carbon and the iodine in that linear part of the SN2 transition state to be horizontal instead of sort of sideways like this. I don't know if I can do that with this. Let's see if I can lasso this. If I can lasso it, and then would it let me rotate it? Nope. No, I can't just rotate this. I can't just rotate that around. So imagine that my NC is partially bonded to the carbon, partially bonded to the iodine. So again, I'm taking sort of this angle and I'm rotating it so that it becomes horizontal. Now, in some other answers that I've given to questions, I have been stressing the idea that if I give you a reactant that has a chiral center and I give you the groups on the bold and dashed wedges, they need to stay in their proper places throughout the mechanism. So that means that the hydrogen is up on a dashed wedge, the methyl group is up on the bold wedge, and then the ring is down here. And just to, again, imagine taking this entire molecule with the CN minus coming in and rotating it up about 30 degrees, or rotating it counterclockwise 30 degrees, and you would get this transition state. And then going into the final product, and the reason that the H and the CH3 stayed on top in their respective dashed and bold wedges is because basically they're on top over here. And so they're staying on top over here. So then we get to the final product, which would have the carbon, the NC group or the CN group attached to the carbon. We would have everything's going to fold to the right. So we have our ring on the regular bond, our methyl group on the bold wedge, and our hydrogen on the dashed wedge, plus then the I minus. So again, and if you look at some of the answers that I've given on in the Piazza, what you'll see is that we always keep those groups on their bold and dashed and regular bonds. We keep them on those bonds throughout, and the molecule goes from being sort of folded to the left, the three bonds to the left, to then being on the right at the end. Now I can double check this and make sure that I'm correct, because hydrogen is 4, methyl group is 3, iodine is 1, and the ring is 2. So in this, at the beginning of this SN2 reaction, going from 1 to 2 to 3, this is the R configuration. So if this truly inverted in an SN2 reaction, this product better be the S configuration. And here's my 4, here's my 3, here's my 2, and here's my 1. And that's, again, it's an N triple bonded to a C. So this carbon has 3 C's. This carbon has 2 C's. This has 1, it has all H's and H. So going now from 1 to 2 to 3 is counterclockwise. So indeed, I did go from R to S. So that's the reason why the methyl and hydrogen stayed on top, is because that's where they were to begin with. But again, when you're doing SN2s, and I also recently put up an example of an SN1. If you get a chiral center as your reactant, and I show you the bold and dashed wedges, those bold and dashed wedges have to stay, the groups have to stay on their appropriate bond all the way through to the end. So I hope that helps.